Okay, our next topic is rationalizing the denominator of a radical expression. We're going to start just first with numerical radicands. We'll talk about variables in a second video. So remember that when we looked at square roots earlier on in the year, we saw that you are not allowed to leave a radical in the denominator. You couldn't have a square root in the denominator. So we had to rationalize. Well, that's true with any type of radical. So we can see here, the rule is you can't leave radicals in the denominator. No radicals in the denominator. So we have to rationalize it. Now, when I say to build up, here's what I mean by that. We are trying to multiply by another radical so that whatever the index of your radical is, that becomes the exponent of the radicand. Because what happens if I have the nth root of a to the n, that comes out to be a. And that's what we're trying to do because now the radical is gone. The nth root of a to the n just takes everything down to just a plain a. So, for example, the fourth root of 6 to the fourth would be just 6. And now there's no more radical. So that's what we're trying to do. Okay, let's look at this example here, and I'm going to actually show you two different ways that you could think about this. Neither is more right than the other. It's just kind of what your preference is. One of them's probably a little bit faster. So let's look at like the guaranteed, always going to work method first. So if we look at the radical that's in the denominator, it's the fourth root of 9. Now this is a 9 to the first. We need it to be 9 to the fourth in order for the radical to cancel out. And so that means that if I were to multiply this by the fourth root of 9 cubed, that would allow me to make it the fourth root of 9 to the fourth. So hopefully you can kind of see why that is. Remember the rule, if I do 9 to the first times 9 to the third, we add the exponents. So I get 9 to the fourth. And since those two radicals have the same index, we're allowed to multiply underneath the radical because that's what our properties say. Whenever we are, this shouldn't be an equal sign, we're multiplying here, sorry. Whenever we are changing a fraction to something else, like in the sense of trying to find a common denominator or anything like that, if we multiply the denominator, we also have to multiply the numerator by the exact same thing. And the reason for that is anything divided by itself is 1. So even though I just multiplied by this fancy looking fraction, all I really did was multiply by 1. And that keeps your original problem exactly the same. That's why we're allowed to do it, and that's why you have to do both the top and the bottom. So here's what's going to happen. Fractions multiply straight across. So in the numerator, I get 4 times the fourth root of 9 cubed, which you can go ahead and do, that's 729, over, using our properties of exponents, we now have the fourth root of 9 to the fourth. Okay, now we need to try and simplify a little bit here. So first thing I want to check is this radical. So go to your fourth power column on your table, and you want to see if there is a perfect fourth that goes into 729. So if you look real hard, you'll find it. It's 83. So this is, 81. This is the fourth root of 81 times the fourth root of 3. That's why I was thinking 3. Because it's going to, 81 times 3, that's not even right. I don't know why I said that. 81 times 9 is 729. 81 is the one that you got from your list. And then when you do 729 divided by 81, we get 9. The reason why we picked this is because this first one is going to be a whole number. So here's what I have in my numerator now. 4 times I'm going to get 3 from the fourth root of 81, and then I still have that fourth root of 9. And then down here in the denominator, because this is a fourth root of 9 to the fourth, we just get 9. And now we can go ahead and try to simplify that. You can multiply those two together if you want, or you could simplify right now. So you could get 12 times the fourth root of 9 over 9. And then remember, we still need to consider our fractions. 12 over 9 does simplify to 4 over 3. And so your final most simplified answer would be this. I know it does not necessarily look more simple, but we decided a whole long time ago that the rule was going to be that there were no radicals in the denominator. And so that's why we have to write it in this form. Okay, I'm going to erase this, and I want to show you a different way that you could think about this. So here's how I would do this problem if I was trying to like save myself on some work. So I always look at what I have. So here I have 9, and I want to see if I can write that as a different power with a smaller base. So for example, I look at 9, and I know that 9 is the same as 3 squared. So I'm going to rewrite this as 4 over the 4th root of 3 squared. The reason why that saves me a little bit of time is because now to get from 2 to 4, I only need another 3 squared. 2 plus 2 is what's going to give me 4. So I'm going to multiply in this scenario by the 4th root of 3 squared. We didn't pick 3 squared because it was the same as this. We picked it because 2 plus 2 equals 4. All right? So now we multiply straight across, and I get 4 times the 4th root of 3 squared, which is 9, over the 4th root of 3 to the 4th, which simplifies down. And so do you see why this ended up being a little bit nicer? Our answer is already simplified by the time we get to that last step. And so if you simplify those radicands into smaller powers, it's always going to work out that way, which is a little bit more helpful. So go ahead, put the video on pause, and try to do example 1 and example 2 on your own. Come back in just a second and check with me to see how you did. So to work through example 1, I'm going to use the shorter method that I was just talking about. So I look at 8, and I know that I can express 8 as 2 to the 3rd power. So I'm going to do that. My numerator isn't going to change. The 5th root of 7 over the 5th root of 2 to the 3rd power. So I have 3. I need to get to 5. So that means I need another squared to add to it. So in order to rationalize this and make it a 5th power, I'm going to multiply by the 5th root of 2 squared in both the numerator and the denominator. And again, that's because 3 plus 2 equals 5, and that's what we want. So if I multiply then straight across, since the top 2 radicals both have the same index, that means we can go ahead and multiply. So I'm going to get the 5th root of, this is going to be 7 times 4, that's what 2 squared is. So we get 28 over, now you can sort of at this point hopefully start thinking ahead. The whole reason that we multiplied by this was to get the radical to cancel out. So you can see we're just going to get 2. And just to kind of recap, the reason why we got 2 is because this is going to give us the 5th root of 2 to the 5th. And that's just going to be 2. And you want to check and see if the 5th root of 28 can be simplified. It can't. So that means this is our answer. Okay? Let's go ahead and look at number 2. The first thing I would do on number 2 is use our properties to split this into a separate numerator and denominator. So this is going to be the cube root of 1 over the cube root of 6. And now the cubed root of 1, any root of 1, is just going to be 1. So we can go ahead and make that a little bit simpler for ourselves. So now on this one, we can look at our radicand of 6, see if we can express that as a power. And we can't. The only exponent that gives us 6 is 6 to the 1st. So that means that if this is a first, I'm going to need 2 more to add up to 3. So we're going to multiply by the cubed root of 6 squared. And so, remember, these 2 were designed to cancel that radical. So we're just going to get 6. And in the numerator, we get the cubed root of 6 squared, which is 36. Now you can check your perfect cubes to see if anything goes into 36. Unfortunately, it doesn't, so that means that this is in its most simplified form. So this is how we can rationalize the denominator when we have numerical values in the radicand.